Hello people and welcome back to another video. In this video, we'll be going over a very pertinent statistical concept called statistical inference. Now, what exactly is statistical inference? Now, in our previous videos, we have discussed about the idea of a sample and a population. There we discussed that a sample is a small chunk of the population. We take a sample from the population to analyze the sample and extrapolate the results to make specific conclusions about the population. Now, what statistical inference is the process of doing or executing this idea. Now, statistical inference is the study of samples where we analyze a sample, we draw some conclusions from that sample, and we extrapolate those results to the entire population. Now, the output or the conclusion of a statistical inference is basically a probabilistic statement which gives an idea of what a population parameter might look like. And this is generated or inferenced from the conclusions drawn from the sample. Now we have some specific tools for statistical inference. We'll be studying two of those tools in detail in the upcoming sessions which will come. So the first tool we have is confidence interval. Now, what exactly confidence interval is? Now, confidence interval basically tells you the range of a population parameter. So we study the sample, and post our study, we have to extrapolate the results to the population. There will be a population parameter which we have to estimate. So what we will do is that from the results that we've gained from the sample, we will give a statement of conclusion where we will say that there is high probability or high confidence that the population parameter lies within this particular range. So the result of a confidence interval is a range. So we'll take a look at an example. So this problem statement reads, suppose a company would like to estimate the average amount of time callers are on hold before they reach a customer service representative. Executives from the company plan to randomly sample 100 calls and use the sample mean X bar to estimate the population mean mu, the average of all callers' wait time. Assume that sigma or standard deviation of the population is 15 minutes and sample mean of the wait times, which is X bar, which is the mean of the sample, is 30.9 minutes. So now we have to make a judgment about the population mean mu. So first of all, let us go ahead and write the details that we have been given. So we have been given the population standard deviation. This is 15 minutes. We have been given the sample mean, which is 30.9. And what do we need to find or what do we need to estimate is the population mean. This is what the problem statement looks like. Now, if you have gone through the module on sampling and central limit theorem, in that module, we discussed a very important idea that if you take a sample out of a population and you repeat that process multiple times, the sampling distribution of the means start behaving like a normal distribution. We also looked at the pertinence of the number of samples chosen. And if the number of samples are greater than 30, then the distribution starts following a normal distribution. The distribution of sample means, or what is also referred to as the sampling distribution. Now, if you haven't gone through that video, I would really urge to watch the previous video where we have discussed sampling and central limit theorem in detail before you come and watch this video. So I'm assuming that you are clear with the concept of sampling and central limit theorem. So I will move on in this particular question. So We have been given the population standard deviation and the sample mean. We know that our sample size is 100. So because our sample size is greater than equal to 30, the sampling distribution will follow a normal distribution. And when that happens, your population mean is equal to the sample mean, and your sample standard deviation x becomes sigma by root n. So this becomes 15 divided by square root of 100, which is nothing but equal to 1.5. Okay. So this concept that I've just explained, all of this is covered in the video where we have gone through the concept of central limit theorem and the concept of sampling. So I'll remove this portion completely. So you have x bar as 30.9. S you know is 1.5. We have just calculated it. And you know that the distribution is normal distribution. So we discussed another concept in normal distribution called the 68, 95, 99.7 rule. Now, according to this rule, you can say that 95% of the data lies within 2 standard deviation from the mean. So, for the population mean, or basically, if I say that we are 95% confident that the population mean lies within 2 standard deviation from the sample mean, because this distribution follows a normal distribution. So the lower bound can be written as 30.9 minus 2 into 1.5, and upper bound is given by 30.9 plus 2 into 1.5. If you do the math, this will come out to be 33.9, and this will come out to be, so this will come out to be 33.9, and this will come out to be 27.9. So you can say that there is 95% confidence that our population parameter lies between 27.9 and 33.9. So this is one of the examples of confidence interval. But here we are 95% sure. What if someone asks me to calculate the 90% confidence interval or the 85% confidence interval? How will I do those sort of problems? Now, for that, we have to generalize the way we calculate confidence interval. So this is the generic formula that we have to calculate the confidence interval. The lower bound is given by estimate minus margin of error, and the upper bound is given by estimate plus the margin of error. Now, Margin of error, this term that you're seeing here, let's call this MOE. Margin of error is given by Z into sigma by root n. You already know sigma by root n is nothing but the sample standard deviation when the sampling distribution follows a normal distribution. Z out here is called the test statistic. Z is called the test statistic. So what is Z statistic? How is it calculated? And what are some of the details and finer nuances in the margin of error? All of that we'll be seeing in our next video. So stay tuned for that. And I thank you all for watching this video.